Okay, so in this section we're going to look at Archimedes' principle. So just imagine you're in Greece, right? And a king presents you with a crown and says, "Is this really gold?" Well, what do? Well, the story is that Archimedes placed it into a bathtub with him and saw that it didn't behave like it should. He jumps out of the bathtub and yells "Eureka!" Right? And so that's kind of the origins of the word Eureka, and he goes running through the streets to tell the king that this crown is fake. It's not gold. Now, is that really how the story goes? Probably not. But what Archimedes knew was he knew shipbuilding. And what he was really doing was developing a ship the size of a city, or the proposed size of a city, so that he can, use it for battle. All right? And so what this is all based on is what is called the buoyant force. So the buoyant force, right, is the net upward force on an object in any fluid. So this force is what is responsible for determining if objects will sink or float. So if the buoyant force is greater than the object's weight, the object will rise, right? So it'll float on top of the water or on top of the liquid, right? If the buoyant force is less than the object's weight, the object will sink, right? Because the fluid can't provide enough of a buoyant force to cause it to rise. All right? Now, if the buoyant force equals the object's weight, then it's just going to remain suspended. Okay, so in diagram form, right, so if I have an object just floating, what that means is that my buoyant force is greater than my weight. Okay, if it's my buoyant force is less than my weight, I will sink. Right, and so in actuality, this object would be down at the bottom of our vessel here. So my FB would be less than my FG. Right, and if they're equal, you can place it anywhere in here and it'll just be suspended, right? It'll look like it's just kind of hanging out in there, right? And so sink, float, rise, okay? Now, where does this come from? This comes from this principle that we know as Archimedes' principle. So Archimedes' principle says that the buoyant force on an object equals the weight of the fluid it displaces. In equation form, it's going to be rho vg, or the density of the liquid times the volume of the liquid displaced times 9.81, where, remember, mass is rho v. Okay? And so again, density, it'll be the density of the fluid, not the object. Right? And V will be the volume displaced. If you remember, if you ever took like an earth science class and a teacher may have asked you what's the density of this odd looking, figure. Well, one of the ways to find the volume is to drop it into water and see how far that water rises, because that's how much that would be the volume of that object. Okay? And so like if I have a graduated cylinder, and I have a rock or an odd shaped object, I want to find out what is the volume of this object. I'm going to note where it is, and then I'm going to put the object in. It should sink to the bottom, and this amount would be my volume, right, of that object, because the volume displaced is equal to the volume of the object. Okay? Now, this says calculate the buoyant force on 10,000 metric tons, 1.00 times 10 to the 7th kilograms of solid steel completely submerged in water, and compare this with the steel's weight. What is the maximum buoyant force that water could exert on this same steel? It says still, but it's just just say steel, if it were shaped into a boat that could displace 1.0 times 10 to the fifth cubic meters of water. Okay, so let's start with the first thing, right? So how much buoyant force would be provided? So we're going to do rho vg. Okay, but what we need to do is find what is the volume of the steel. Okay, so volume of steel would be the mass of steel, 1.00 times 10 to the 7th, divided by the density of steel, which if you go way back to the first or second page, we find that 7.8 times 10 to the 3 kilograms per cubic meter. So it tells us that there are 1,282 cubic meters of steel. And so I'm just going to plug that in. So what that means is if I have this much steel, it's going to displace that much water, right? And so I'm going to do 1,000 times 1282 times 9.81, and that's going to give me 1.26 times 10 to the 7th newtons worth of steel, of buoyant force. Now this does say compare it to the steel's weight. So how do I compare that to the steel's weight? I just take that 1.0 times 10 to the 7th kilograms, multiply it by 9.81, and it's roughly going to give me 9.81 times 10 to the 7th newtons. So what you'll see is the buoyant force that's provided is not able to hold up that weight, right? Now, what happens if we take that steel and then shape it into a boat where it displaces now 1.00 times 10 to the 5th cubic meters of water, okay? And so all we're going to do is do our rho Vg. So rho Vg. So 1,000, again, water. Volume is going to be 1.0 times 10 to the 5th, right? And then we're going to multiply by that 9.81. And so you find that you get 9.81 times 10 to the 8th newtons, right? So that should be able to hold it at this point in time, right? 9.81. Let me just make sure. One, two, three, four, five, six, seven. Yep. So you can see once we shape it into a boat now, the water is able to provide 9.81 times 10 to the 8th newtons worth of buoyant force, which now the object, right, this metric ton of steel, is able to withstand or withhold, right, that buoyant force, okay, or the buoyant force is able to withstand that steel, okay. Now, density does play a huge role, right, in Archimedes' principle. So the average density of an object ultimately determines whether it floats, right? If the average density is less than that of the surrounding, it will float, which means the buoyant force provided by the fluid is greater than the weight of the object. And there's another thing that you run into here, something called specific gravity. And so what it really is the ratio of the density of the object to a fluid, which is usually water. And so specific gravity is the density of the fluid, or density of the object divided by the density of water. And what this does just tells you, in fact, you can put a sub-zero here, right? And so this is object, water, okay? Now, because specific gravity is a ratio, sometimes they'll do it in a couple ways. They'll use fraction submerged, or they'll do percent submerged. All the same thing. If you're given percent, you need to turn it back into a fraction. Okay. And so suppose you have a 60 kilogram woman floating in fresh water with 97% of her volume submerged when her lungs are full of air. What is her average density? Right. So here, instead of specific gravity, we would call this fraction submerged, which means we would need to convert this. Right. So we're going to do the density of the object is going to be the fraction submerged times the density of water. Right. And so the fraction submerged would be 0.970, and we're going to multiply that by 1,000, and she would have an average density of 970 kilograms per cubic meter. Again, right here, we know her density has to be less than a water because it tells us that she floats. Okay. Now, Archimedes' principle does state that the buoyant force on the object equals the weight of the fluid displaced. So that means that the object appears to weigh less, right, when submerged. So if I took an object and hung it from a spring scale, right, it would have one weight here, but then if I put that into the water, right, it would have a different weight, because essentially what's happening is the buoyant force is providing an upward force, which causes this now to something called apparent weight, which we talked about way back with elevators, okay, where we can determine all kinds of things. We can find the density, we can find the volume, we can find everything, just like we did before, okay. And the reason why I say it appears to weigh less is because technically it doesn't weigh less. It's just that the buoyant force is actually taken away from the weight in air. So the object suffers an apparent weight loss equal to the weight of the fluid displaced. And so apparent weight loss equals weight of the fluid. Right? So delta Fg equals the weight of the fluid, which is rho Vg, or delta M equals rho V, right? So you can do all kinds of, like, algebra with equations that we've used in the past, right? So here this one says the mass of an ancient coin is determined in air to be 8.630 grams when the coin is submerged in water. Its apparent mass is 7.800 grams. Calculate its density, given that water has a density of 1 gram per cubic centimeter, and that effects caused by the wire suspending the coin are negligible. Okay, and so what we can do here is let's find the change in mass by doing rho v. Again, we're looking at this. The volume would be the water, right, displaced. Okay, and so what we're going to do is we're going to say volume equals change in mass over density, and so it's 8.630 minus times 10 to the negative 3 minus we can do this in let's do it in cubic meters. All right, so let me just write this a little bit nicer. I apologize, jumping ahead of myself. I wrote some different things and my brain did something else. So times 10 to the negative 3 minus 7.800 times 10 to the negative 3 divided by 1,000, right? So this will give us in cubic meters, so 8.3 times 10 to the negative 7th cubic meters. And now we can find the density, because now we have the volume displaced, so we have the volume of the coin, and so we're going to do mass over volume, and so we know in air it weighs 8.630 times 10 to the negative 3 kilograms divided by 8.3 times 10 to the negative 7th cubic meters. And we're going to get a density of 1.04 times 10 to the 5th kilograms per cubic meter, or right, and so that would be the density of this coin. So if we put this coin in water, right, that number seems way too high for what I have here. Let me just think on this and double check this. Oh, okay, yeah, because it's being suspended by a coin, or by a wire. Yep, okay. So yes, so this will be 1.04 times 10 to the 5th, right? So this really ends static fluids, and the rest of the unit we're going to look at what happens when the fluids now begin to actually move and flow.